Okay. So, having studied how the momentum term influences the learning process, since we want to get accelerated convergence, we can introduce the momentum term and we can see how that term along with the update that we have using the gradient descent, how this can control the synaptic weight adaptation, and we saw the sketch through a simple signal flow graph how the parameters can influence the rate of learning. One of the important consequences in any algorithm would be the stopping criterion, right. When we think about algorithms that are based upon convergence, right, or iterative algorithms, there should be a mode for convergence. There should be a, I would say rather, a criterion for convergence, not a mode. There should be a criterion for convergence when we discuss iterative algorithms. So, here are some general heuristics one can adopt towards the stopping criterion. So, the first and an easy criterion would be that we fix the number of iterations and we stop. This can be useful particularly in hardware constraints, but you should be very clear about where the initial conditions are, because if you do not know the initial conditions, you do not know where the algorithm will land itself, right. So, if we fix the number of iterations, particularly in the case of hardware constraints, we may have like 25 iterations or 30 iterations based on hardware constraints. If we know the initial conditions well, we know how to progress and then how the algorithm will proceed, at least depending on initial conditions. Otherwise, if your initial conditions are bad, 25 iterations or 30 iterations may not fetch you anything. So, therefore, if you have a good initial condition, you can fix the number of iterations and you can stop. Along with this simple stopping criterion, there are other criteria for stopping. So, let us discuss some of these. The first criteria is stop the algorithm when the Euclidean norm of the gradient vector reaches a small threshold. That is, I take the gradient of the error with respect to the weight, I get the adaptation done and I have the weight vector at time n plus 1, and over subsequent iterations, if the difference vector, that is w n plus 1 minus w n, is within an epsilon threshold, that is it might just rattle when you take the norm of w n plus 1 minus w n, it may rattle, but as long as within an epsilon threshold, as long as within an epsilon threshold, we can say that we have reached convergence and we can stop somewhere. The second criterion is as follows. So, BPA is considered to converge when the absolute rate of change in the average square error per epoch is sufficiently small. Right, I repeat again, the absolute rate of change in the average square error, that means I am plotting this error as a function of iteration n. I call it j, or if you want you may call it e of j of n, or some other notation. I would say the error energy, average error energy over the samples. I plot this as a function of iterations, and in the case of batch mode it may be an epoch. So, it may start with some value and finally it might rattle and come down. So, if I am within some epsilon tolerance here, typically 1e minus 2 or 1e minus 3, then I can stop. This is another practical constraint. So, whichever criterion you like to choose, you have to bear in mind that the error should be sort of small when you stop. Second is direct. In the first, if there is no much change in the norm of the gradient vector, there is nothing that you can do about it, it is basically stopping there. So, therefore, you can kind of assume that it is converged, but the geometric field is when you are tangent to this surface, the gradient is basically 0, you are pointing flat to the error surface, and there is nothing much you can do about it because you have reached this saddle point anyway, and that is the criterion. In the case of hardware, criterion 1 and 2 may be difficult because of finite resources in the hardware, right, because you may have finite resources in the hardware in terms of the power consumption, in terms of throughput and all these things. In such a case, you fix the number of iterations, but you have to be clever to choose the initial conditions for the weights appropriately. This can be through a hardware software combination. Basically, if you have a software which would run the algorithm in some way that would set up the initial conditions appropriately, then you can plug that initial condition to the hardware for a faster convergence, right. These are some practical considerations that one has to adopt, and I am stressing also on hardware in this course slightly. I mean, though I do not discuss any systems related stuff related to neural networks or hardware systems related to neural networks, but I think it should be sort of evident because people are thinking about hardware implementations of these systems. Now, let us summarize the backpropagation algorithm, right. Having studied the derivation of the algorithm, considered the role of the activation function towards computing the derivatives and making simplifications, understanding the role of the learning rate, right, including the momentum term and the stopping criteria, etc. Let us summarize the backpropagation algorithm. It is pretty straightforward if you have digested the derivation of the algorithm from first principles. So, the first step would be initialization. Assuming no a priori information on the synaptic weights, pick up the synaptic weights in threshold from a uniform distribution with 0 mean and some small variance to make the local reception fields lie within the linear part of the sigmoid activation function. This is sort of a, it is a heuristic. Okay. Then presentation of the training samples. On a per epoch basis, shuffle the data points and present this to the network, right, because when you are learning, if you are feeding it sequentially, there may be a certain bias you may be inherently introducing with respect to the time order. So, therefore, if you shuffle the inputs, randomize them and then present it to the network can adapt better. Okay. This is one of the important steps. Now, as I discussed earlier, we have forward computation step and the backward computation step. Now, consider a tuple xn dn, this is our feature vector. So, given real life signals such as speech, images, etc., we can extract features out of them, feature vectors. A good example of a feature vector would be the Parcour coefficients or the partial correlation coefficients that you can compute as a result of the linear prediction of a signal, of a speech signal, of a windowed speech signal over an interval, right. I mean, take a speech signal, window it, over the windowed signal you can compute the linear prediction model and then basically get the Parcour coefficients, right, or LPC coefficients. So, these can be feature vectors. Similarly, for images you can get some statistics at different orientations, etc. These are all feature vectors. So, raw signals will consume lot of data, but when you extract features out of them, you can compactly represent the signals and you can use those features and stack them as feature vector. You can use those features as feature vectors, and this one feature vector would be one data point for this neural network. So, corresponding to the feature vector, you also have the desired vector, or I would say desired response vector. These are given as inputs to the neural network. We compute the induced local fields and the functional signals of the network in a feed forward manner, layer by layer, right. This is important, just sort of recapping what we did. Now, for a layer L in general and a neuron J within layer L, Vj of L at time instant n is summation I equals 1 to m suffix L minus 1. This is basically number of neurons in the L minus first layer excluding bias. Okay. So, I basically scale all the functional signals from neurons I from 1 to m suffix L minus 1 in layer L minus 1 with the corresponding synaptic weights. So, this is sort of straightforward. Now, for the output layer, small l is capital L. So, Yj in layer capital L is basically Oj, which are these outputs. I mentioned Oj because we discuss activation functions, and from there we derive, we discuss them as outputs, and then it is easy for us to compute the local gradients. So, we bring in this notation Oj for outputs. For inputs, Yj in layer 0 in the input layer is basically Xj. This is for all the inputs excluding the bias. For bias, we have to treat them separately. The 0th coordinate in all the layers, right, from 1 through L minus, from 0 through L minus 1. So, this is initialized to plus 1. This is basically hard wiring the bias, hardwire 1, you hardwire the 1, you hardwire as 1 for these inputs, but the bias is, this is variable, right. Wj0 in layer L at time instant n is basically this bias Bj, right. So, because we want to connect from plus 1 through this weight Wj0 L, right, this is what we need to compute, which is basically I will put this in this form, Bj L Fen is defined to be your Wj0 at time n layer L, right. So, this is variable, and of course, this is hardwired and this is constant, which is fixed. Okay. Now, we compute the error signal, which is Ej of n is Dj of n minus Oj of n. You know what Dj is because it is supplied to you. Oj you can compute because of the forward computation step, which is terminating in the last layer. So, you can compute the errors this way by evaluations in the feed forward computational steps. The backward computation starts from the last layer. So, we start with layer L equals capital L, small l equals capital L, compute the local gradient at layer capital L given by the error that you see at node j in layer capital L times the derivative of the activation function evaluated at the local reception field for node j in layer L, right. This is straightforward, and for all the layers from 1 to capital L minus 1 you do using this computation. This is again reinforcing the signal flow graph. I think by now I must have reinforced this more than 3 times already. So, you have to basically take the local gradients at layer L plus 1, scale them by the synaptic weights, connecting a node in the L plus a node k in the L plus first layer to a node j in layer L, right, and basically you take the summation from k equals L 1 to L plus 1 m suffix L plus 1. So, this is number of neurons in the L plus first layer, right, and then you scale this with the derivative of the activation function evaluated over the local reception field at that particular node, that is node j, right. In the single layer case, this L was 1 and this L was 2 here, L plus 1 was 2. So, we could do this, but for any arbitrary number of layers you can follow these steps very carefully. So, this is how it would go. So, this red indicates that you are starting at layer capital L and you progress in this direction and you go from L plus first layer, Lth layer dot 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 all the way till you reach the first layer, right. So, once you have the deltas, then you can compute the weights. So, we adjust the synaptic weights as per the general delta rule. If you follow the gradient descent, you just get this. The local gradient times the functional signal, because that is the input. If you do the momentum push, you bring in this alpha parameter and you regress based upon the synaptic weight at a previous time instant, right, and this is Wji, this is delta, Wji at n plus 1 minus Wji at time n is basically your delta. So, this is your delta. Okay. So, given the momentum parameter alpha and learning rate which is eta, you can adjust your synaptic weights. And iterations. You loop forward and backward with the computational steps that I described under steps 3 and 4 until the stopping criterion is reached. And how you choose the stopping criterion, I discussed all the steps towards stopping the algorithm. It could be fixed number of iterations, or when I reach an epsilon tolerance in the error, or when the norm, the difference of the norm of the weights over subsequent iterations is within an epsilon threshold, and epsilon is a positive quantity. Okay. So, whichever is the criterion that you find it useful, you can adopt that criterion, but beware of the details of the variables therein. Having derived the backpropagation algorithm and having distilled the details of how the computation steps follow, let us look into the heuristics to make the backpropagation algorithm work better. So, we have some general rules, these are rules of thumb and they are heuristics. The first heuristic is stochastic versus batch update. So, depending upon the redundancy in the data, we can opt for the stochastic algorithm, and if we want a more refined version where we accommodate for all the errors within the exemplars, then we have to go with the batch update. So, this again depends upon the choice of the algorithmic conditions that you are interested in practice. Next would be maximum information content. We may want to use examples that provide the largest training errors. because I think these are the outliers and you want to capture that information content within the network. This also means that we can have radically different data points, I mean again to substantiate that they could be outliers. Next, input data shuffling. You may want to shuffle the data and present it to the network, then keep the same time order for the data samples that were presented in a previous epoch. So, shuffling can give you more entropy, so it is good to sort of shuffle and present it to the network so that it has that plasticity to learn the examples. Choice of activation function and range. Typically we would like to have the range within the sigmoidal linear region. So, this is where we would like to operate and not get into the saturation. And again, if you think about the activation function, there are various choice of activation functions and one can try different possibilities that works best with the system. I would also like to pinpoint to you that in convolution neural networks having multiple layers, the rectified linear unit, that is the choice of the activation function than the sigmoid or the tan hyperbolic. So, there are reasons and we will talk about those when we get there. The next heuristic, this would be normalizing inputs. I think this is sort of obvious. If you are, for example, we have data vectors and one data vector is in a range from say 0 to 1000, another is from say maybe 10,000 to 100,000, so on and so forth, then it is good to often normalize these inputs in certain ways so that we are operating on the same normalized conditions, right. Otherwise we will blow up the updates because of the inputs. And normalization will align the direction because you are only scaling the inputs, but you are preserving the direction, the directivity is not lost. So, therefore, it often helps normalizing the inputs. Weight initialization. So, we discussed earlier that we can have weights chosen from a uniform distribution with 0 mean and variance which is well contained within the range of the sigmoidal activation function, right. So, what would be the choice of other distributions? Do we want uniform distribution? Do we go with other choices, maybe Gaussian distribution, so on. So, this again is a heuristic. So, whatever works best for the system has to be explored, right. In general, we choose weights that are initially from a random distribution and not the all 0 input. What about learning rates? I mentioned to you earlier that learning rate plays a very important role. Typically one can fix the learning rate to be constant, that is it is a small value between 0 and 1, something like 0.01, 0.05 depending upon the conditions and the data, etc. But one may question that if you want better convergence, etc., you may want to go with adaptive learning rates where each neuron has a learning rate which depends on the data it sees and the conditions it sees, right. So, therefore, having adaptive learning rates will help individual neurons align faster to the optimal solution. So, these are some of the heuristics, and when you code the algorithm and when you experiment, you may want to choose several of these heuristics and see which works better for your system. So, this sort of summarizes the backpropagation algorithm. So, I have outlined the computational steps. So, you can follow these as a recipe and you can basically do the computations and you can code it up. The best way to learn any algorithm would be to try these through examples. So, I suggest that you play with the data, write your own code. There are all toolboxes available through MATLAB, Python, etc. But the best way to learn these systems is to code the algorithm yourself, get a handle to the variables and then analyze the dynamics of the algorithm through simulations and through mathematics, and you will feel you will get a feel for the algorithm. Okay. Let us get started with the XOR problem. So, the XOR problem is stated as follows, right. We all know what an XOR gate does. So, it is a basic fundamental gate working with Boolean variables with 2 inputs. So, we will just consider a 2 input XOR gate. Now, so we assume Boolean variables here which are x1 and x2, right. So, we will do this computation first. 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. So, we just know what the 2 input XOR gate does. Now, what we do is the following. We will group all the zeros that we get as one class, all the zeros that is the outputs are class 1, all the ones are class 2. Okay. Now, I grep out these 2 conditions and this forms class 1, and similarly I grep out these 2 conditions, they form class 2. Now, just put on a 2 dimensional plane. So, I have variables x1 and x2 on my axis. So, I put these points, right, 0 0 is here, 1 0 is here, 0 1 is here, and 1 1 is here, right. Now, these 0 0 and 1 1 they form class 1, which is indicated by these zeros, and I will use another color here. The 1 0 and the 0 1 give us these outputs, 1 indicated by x or this x mark as class 2. Now, our goal would be to basically figure out a classifier to classify these points, and we clearly know from the perceptron example that we cannot have one hyperplane that can separate these classes, right. Think about a hyperplane here. If I put here, I can't have perfect separation, right. So, I can't do linear separability using a single perceptron. So, I will write it here. One cannot get linear separability with just one hyperplane. In this case, the hyperplane is just a line. So, now let us see how we can do this using the multi-layer perceptron idea, using hidden neurons, etc., and we will go through the details of the solution to the XOR problem and generalize this to the 3 variable case.